Hello students, this is Dr. Faizan Mirza. Here we'll be covering transport across the membrane, not through membrane, because transport through membrane occurs by diffusion, osmosis and active transport, whereas transport across membrane involves bulk transport. Bulk transport means that the movement of substances will be occurring in the large quantity at one time. This can either be occurring by endocytosis or exocytosis. When we are discussing with bulk transport, it occurs either by endocytosis or exocytosis. Endocytosis and exocytosis both are receptor mediated, which means there are protein receptors present on the membrane which are involved in causing exocytosis or endocytosis. Endocytosis could either be pinocytosis or phagocytosis. Pinocytosis is cell drinking and phagocytosis is cell eating, which means that in pinocytosis the cell takes up the liquid particles in large quantity. In phagocytosis the cell takes up the solid particles. In endocytosis, there are proteins present at the cell surface membrane. This is the ECF and ICF. These are called clathrin-coated pits. The clathrin-coated pits are where the substance will start to attach, which needs to undergo endocytosis. The actin and myosin contracts along the inside of the cell at the ICF surface. The membranes start to involute. Invagination occurs, and as it involutes, a vesicle pinches in. The vesicle is coated by the clathrin proteins, you can see, and this is the vesicle. This is the phagosome. This is called a phagosome. So, and this is a temporary vesicle in which the substance that was endocytized has entered into the cell. So vesicle is engulfed. In exocytosis, we see released substances upon certain stimulus, and the exocytosis allow neurotransmitter, enzyme, and hormones to go out from the cell cytoplasm outside the cell. The summary so far is that transport can occur through the membrane or across the membrane. Through the membrane could either be passive or active. Passive could be diffusion or osmosis. Diffusion could be simple or facilitated. Active could be primary or active transport or secondary active transport. All these three are protein mediated. Across the membrane could either be endocytosis or exocytosis. Endocytosis is pinocytosis and phagocytosis, and these are protein mediated as well. Starting our discussion of the Ligand-gated channel. A Ligand-gated channel is one which will open up or close in response to a ligand being attached or detached from the channel. So for example, if this is the phospholipid bilayer and this is the Ligand-gated channel here, this Ligand-gated channel is the one which is having acetylcholine binding sites. There you can see this particular channel. It's having subunits here. It's having 2 alpha subunits, 2 beta subunits, and it's having a gamma subunit as well. So this is how this channel is working, and when it's working here, we can see that the acetylcholine receptors, these 2 binding sites of alpha subunit allows 2 acetylcholine molecules to sit across it. When 2 acetylcholine molecules can attach, a channel can open up. We know that sodium is outside high and chloride is high as well. One is positive charge, the other is negative in charge. And inside the cell, there is a negative membrane potential. Outside the cell, there is a positive charge. This is the RMP present in the membrane. Inside the cell, you have a low sodium and a low chloride concentration. So if 2 acetylcholine attaches here, the pore can open up. The pore can allow the movement of either sodium or chloride ion, and this is called sodium influx or chloride influx. The sodium potassium, this Ligand-gated channel is having 5 subunits, 2 alpha, 2 beta, and 1 gamma, as I have just mentioned. And the 2 acetylcholine binding sites both are on each alpha subunit. Acetylcholine just attaches to this acts as a ligand. The pore diameter is about 0.65 nanometer. Acetylcholine receptor is 25,000 Daltons. Sodium influx will depolarize the membrane, whereas chloride influx can cause hyperpolarization. So in a depolarized state, we say the cell becomes excitatory, or in hyperpolarization becomes inhibitory. In case of depolarization, excitatory post-synaptic potential is generated, which means that the resting membrane potential becomes, from the resting membrane potential, which is a negative value, it goes to a positive value, and the cell becomes depolarized because of the sodium ion coming. Whereas if the cell was at RMP and instead of sodium ion, the chloride ion enters, so this would have been an inhibitory post-synaptic potential, which means the resting membrane potential was already negative. If chloride ions entered the cell, it will cause the membrane potential to become even more polarized, even more negative. So this is called as hyperpolarized state, and that's inhibitory condition. This is the overall summary of the membrane channels and transport. This is the leak channel I'm showing to you. Passive channel, these are the voltage gated channel. This is the sodium potassium pump, the glucose co-transporters and antiporters. All these are assembled on the membrane at once. So you can see ECF and ICF have all the proteins present on the cell surface membrane. Some passive channels, some pumps, some voltage gated channels, some sodium potassium pump, everything is there on the membrane. And you can see that the passive channels, they allow the movement of substances down the gradient. The sodium potassium pump allows the movement of substances, that's the sodium and potassium ion in this particular direction against the gradient. Sodium goes out, potassium comes in. I have added these two symbols here, one steric and one tick mark, to point out which one is the carrier protein, which is the channel protein. And you can see this is a channel protein. This is a channel protein. This is a channel protein. So the channel, this is also a channel protein, but this is the gated channel protein. The gate is closed. So the channel protein could, this is also a gated channel protein. So a channel protein could either be gated or leaked. This is the gated protein channel, which is gated. The gate is closed. This is a leak channel, which is opened. Whereas these are all carrier protein. A carrier protein will not have a pore present all across it. This is also a gated channel, but this gated channel is gated by the ligand. If the ligand will attach here, the channel will open up. This gate is controlled by the changes in voltage. So we can have voltage gated channel. This is a voltage gated channel. This is also a voltage gated channel. These are the ligand gated channels. Whereas these are carrier proteins. We know that carrier protein do not have a pore or a passageway running through its length, whereas a channel protein will always have a pore running all along its length that can allow a certain substance to cross down the gradient, whereas the carrier protein brings about a conformational change, and only then it can cause the movement of substances to occur. This here shows to you a three-dimensional diagram of how the phospholipid bilayer is arranged and how the membrane proteins are there. So this is a glycoprotein, this is the ECF surface, this is the ICF surface. This diagram I've just added to give you an understanding of how the proteins are embedded in the membrane, and this is how they are arranged. Like a membrane can have a wide variety of protein which are mediating different solute transport. That's it from my side. Thank you so much.